So it's my pleasure to introduce Tal, who's visiting us from Tel Aviv University. He's a computer science PhD student advised by Professor Yishai Mansour. He's done research internships at Amazon and Bosch, and he's also, his main interests are reinforcement learning, online learning, and multi-armed bandits, which is an intersection of those two. So with that, take it away, Tal.
All right. So thank you for the introduction, and thank you for having me. I'm very happy to be here. So this talk is about recent work of myself together with my advisor Yishai Mansour. So what are we going to talk about today? So first, I'll give some background on reinforcement learning, and I'll give the problem setup. I'm guessing that many of you are familiar with that. Then I'll talk about aggregate bandit feedback. This is the main topic of the talk. I'll explain what aggregate bandit feedback is and why do we want to consider it. Then we'll cover some previous approach for how to handle aggregate bandit feedback, and for last we will present our algorithmic approach. Okay, so reinforcement learning. So basically, reinforcement learning we have an agent that interacts with an environment in order to minimize its cumulative cost. Some examples of some success of reinforcement learning. So there's the famous AlphaGo algorithm, which is based on reinforcement learning. Some applications are in robotics, and also recently the fine-tuning of large language models such as ChatGPT, Gemini, and etc. So the fine-tuning of these models is done using our reinforcement learning algorithms. So here's the basic setup of reinforcement learning. So we have an agent that interacts with an environment. We will consider an episodic setting, finite horizon. So basically we run for T episodes, capital T episodes. At the beginning of each episode, the agent chooses some policy. Then a loss function is chosen for this episode. We'll talk in a minute how this loss function is chosen. And then we run the policy on a Markov decision process. This is the MDP. So in a Markov decision process, we start with some initial state S1. Okay, so for h equal 1, we have here S1. And then in each intermediate step within the episode, we sample an action from the policy, which depends on the state, and we transition to some new state, which depends. The transition probability depends on the current state and the current chosen action. Then in the standard model, the standard feedback model, which we call semi-bandit, we observe the loss for each step within the trajectory. So in each state action pair that we visit, we observe the loss function. So this is the basic model. So how is the loss function is chosen? So in many cases, the losses are assumed to be stochastic. That is, there is some underlying distribution that depends on the state, the action, and the time step. And the losses in each episode are sampled IID from this distribution. Okay, but this is a relatively restrictive assumption, and we want to generalize for more general distributions. Distribution that might have correlations between different time steps, between different states. In practice, distribution may shift over time, and etc. So in order to handle any kind of distribution, we would consider adversarial losses. Okay, so basically we would have an adversary that would choose the loss functions. Okay, in arbitrary way. In particular, it can do all kind of correlations between time steps, between states, and so on. If we can handle this kind of adversary, we can handle any kind of distribution. Okay. Okay. And the performance measure. So this is a mainly theoretical work. So the performance measure would be the regret. So V here, Vt of a policy pi is the expected cost of policy pi with respect to the cost function Lt. So we would look at the total expected cost over T episodes of the policy compared to the total expected cost of the best policy in hindsight. Yeah.
Are you going to regularize pi, or are you going to draw that from some class?
So it's going to be a tabular setting. So so basically, we'd consider all possible policies. Okay. Okay, and the goal is to achieve sublinear regret. The lower, the better, obviously. And why sublinear regret? Because if we have sublinear regret, so at least on average, our policy, on average over the T episodes, our policy is as good as the best policy in hindsight, up to some additive term which vanishes with T. Right? Yeah.
Is there any assumption of the loss function, like smoothness, convexity, or?
The loss function could be anything. Yeah, but again, it's a tabular setting. So it's basically for each state in action, it has a number, which is the loss. Okay. It's not continuous or anything. Okay. So as mentioned, the standard RL framework assumes semi-bandit feedback. So again, semi-bandit means that in each state and action that we visit, we observe the loss. And this does make sense in many cases, but in some application, it is not a realistic assumption. So let's consider this chatbot example. Okay, so as mentioned, large language models are now trained with RL algorithms, which is basically, if you think of say a multi-turn conversation, it's basically modeled as an MDP. So in every time step, the response of the chatbot is like an action we choose, and then the prompts, the user prompts are basically the states, the state transitions. Okay, so consider this example of a flight bot. So we might say want to book a flight. So we ask for the robot to help us book a flight, and then it might ask, all right, where do you want to go, in which dates, and so on. I might tell him. It might ask me additional questions, and at the end, you know, at the end he does something, right? And I might get this kind of survey that would ask me how was my overall experience. Okay. Now the thing is that basically the user gives a feedback only for the full conversation, right? It doesn't give the feedback for each response of the robot. All right. So this is like so in this example we don't have semi-bandit feedback, right? We only observe the full trajectory loss. Okay. Yeah.
How is this different from just having a sparse loss function? You know that you only, when you reach the goal, you get points and everywhere else you don't?
It's not really about it's not really about a goal here, right? I might have intermediate rewards. I mean, some intermediate response here might be the thing that I looked for or improved my experience, right?
So I guess you could incorporate that in this. I guess you could maybe incorporate that in the state. That basically the state carries it all around, just doesn't tell you.
Right.
And finally, at the end, you get this reward. With
Yeah. So you can always incorporate things in the state. If you want to incorporate the full trajectory in the state, then it gets exponential, right, in the horizon. So we want to avoid that. Okay. So this is the main motivation, and with this motivation in hand, here is the model that we're going to consider. So most of it is the same. So we run for T episodes for finite horizon. The beginning of each episode, the agent chooses the policy. The adversary chooses a cost function. The policy is executed on the MDP. But instead of observing the loss in each state in action, at the end of the trajectory, we observe, at the end of the episode, we observe the full trajectory loss. That is the sum of the losses. Okay. So any questions about the model itself? Okay. So before we move on, I want to give you some overview of the results that was done so far and how we improved them. So first, if you have if you know the dynamics of the MDP, if you know the transition function, one thing that you can do is to reduce this problem to the problem of linear bandits. I'll show this reduction in a few slides. And then you would get this regret guarantee. Okay, so in these regimes where we have non-dynamics and adversarial losses, we improve this by a factor of SA. So S here is the number of states, A is the number of actions. So a factor of square root of SA. And we also show a matching lower bound. So essentially, we show that this regret bound is optimal. In the stochastic regime, so the first paper that considered this kind of feedback was with stochastic losses and unknown dynamics. They achieved this regret bound. And recently, Kasser et al. Considered the model of linear MDPs. So in linear MDPs, basically each state and action is associated with some vector. And then both the cost and the transition is linear with respect to this feature of the state and actions, this feature vector. Okay, in this case they get this regret bound, and in the special case of tabular MDPs, they show a similar guarantee to Efron et al. Here. So this is in the stochastic regime. In our model, where we have unknown dynamics and adversarial losses, the previous paper that considered this model was by Cohen et al. From 2029. And they achieved this regret bound, which is far from optimal. In particular, the dependency in the number of states is like s to the power of 6. And we significantly improved that. This is not optimal yet, or we don't know that it's optimal yet. And our algorithm is more efficient, and I would say that also more natural as a reinforcement learning algorithm. Yeah.
In the unknown stochastic setting, what is D?
Here, so this is in linear MDPs. D here is the dimension of the feature mapping. So each state and action is mapped to some d-dimensional vector. Yeah. So this is not what we consider. Just.
Is it independent of the number of states and actions in that case?
Right. So the regret here is independent of the number of states action. It depends
because
on the dimension.
It somehow incorporates the action space of these.
Yeah, exactly. Okay. So what we're going to do now, so I'll show this reduction to linear bandits. I'll also show briefly what Cohen et al. Did, which is in the setting that we consider here. And then we'll talk about our algorithms. Okay.
Sorry, just what is distorted linear bandit?
Right, so I'll talk about it. So basically in the non-dynamics case, you can reduce it to linear bandits. You can't reduce, in the non-dynamics case, you can't reduce it to linear bandits. So they introduce a variant of linear bandits, which they call distorted linear bandits. I'll talk about it. Okay, so before we talk about the reduction to linear bandits, let's talk about what is linear bandits. So in linear bandits, we have a set of action, d-dimensional action, and a set of losses, also d-dimensional. Then we run for t rounds. In each round, we choose an action, a vector, essentially. Then the adversary chooses a loss function, a loss vector. And then the loss that the player incur and observe is the inner product between the action and the loss. Okay? And we assume that these losses are bounded by some B's. So what's known for linear bandits? So basically the optimal bound is b square root dt log n whenever we have a finite set of n actions. If we want to solve that for general convex set of actions, we can do that also efficiently with regret of bd square root of t. Okay? Now we'll show how to reduce that to how to reduce online MDPs to linear bandits. Okay, so this problem of linear bandits is clear? Okay, so the reduction follows a concept that is called occupancy measure. So I think this was introduced first by Zimmer et al. In 2013. Basically, an occupancy measure is a vector of probabilities where so an occupancy measure is associated with a policy pi. Basically, the occupancy measure at SA and step H is the probability to visit state S, take action A in step H. Okay, so this is just a vector of probabilities, and then can be shown that there's a one-to-one mapping between policies and occupancy measures. Okay, so obviously if I know the dynamics, I'm in the non-dynamics case, if I have a policy, I can compute its occupancy measure. That's trivial, but also the other way around, it's using base rule, I can do the other way around. Given the occupancy measure, I can extract the policy. Okay, and moreover, this set of occupancy measures, it can be shown that it's a convex set. Okay, so I can optimize. Okay, so it's a convex set, and moreover, the loss, the expected loss, is a linear function of the occupancy measure, right? If I want to compute the expected loss, I would take every possible loss. Multiplied by the probability for that loss and sum over the losses, right? So the expected loss is simply linear with respect to the occupancy measure, and therefore we can apply a linear bandits algorithm, right? Because I can, instead of optimizing over policies, I can optimize over occupancy measures. Okay, I know this convex set of occupancy measure. The loss is linear, and so I can run a linear bandit algorithm here. Okay. So the dimension here, the dimension of this linear bandit problem is HSA. The losses are bounded by H, the horizon of the MDP, and so this results in regret of H square SA square root of T. Okay. This is due to these results for general convex set. Okay, and this can also be done efficiently. Yes.
Wait, why is it H squared? It should be H squared S
Because the losses are also bounded by H and not by 1. Okay, and so again, this can be done efficiently. The next question that you might ask is, what about unknown P? Can we do this? Take this approach to unknown P? And indeed, this is what Cohen et al. Here tried to do. Okay, so let's see why this is not. We can't do that exactly. We can't reduce the problem with unknown P to linear bandits. Okay, and what we can do instead. Okay, so this concept of occupancy measures also extends to the unknown dynamics case. What we need to do is now so the occupancy measure would be a function of both the policy and some transition estimate. Okay, so it would encode both a policy and a transition, and it would represent triplets. Okay, so the occupancy measure at time H is state S, action A, and state S prime is the probability to visit S at time H, take action A, and then transition to S prime. Okay, and similar to before, now we have a bijection between occupancy measures and a pair of policy and a transition function. Okay, yeah.
So the reason you need, that the previous one doesn't work is you need it to be able to go from the mu back to the pi, like you're gonna do an update step and you have to go back to the policy? That's why you need to know that, with the previous one, why you needed to know
Why do I need to know the transition?
right, is it because,
Right,
because you're updating
exactly.
in the space of the convex set? and you have to
Also from
look back.
pi to mu, you need to know, from pi to mu, you also need to know the transition, right? Because this probability also depends on the dynamics.
Yeah, I guess that's true, okay.
Yeah, but now this vector encodes both the dynamics and the policy. Okay, so given both dynamics, not the true dynamics, but yeah. So given a policy and some transition function, I can compute its occupancy measure, and vice versa. And if I have some confidence bound on the transitions, say that PT would be, say for example, the empirical transition function. And if I have some confidence radius around it, so if I would consider all the transitions that are close enough to this empirical transition, if I choose epsilon properly, I would guarantee that also the actual transition, at least with high probability, is in this function, is in this set. Okay, so if I consider all the set of all these of transitions, so the set of all occupancy measures that associate with some policy and some transition function in this set is also a convex set. Okay, so it sounds like we can optimize over this set. But there is a small problem here. Here is the learning framework that is going to be done. So I'm going to choose an occupancy measure in this set, but this is not the actual dynamics of the MDP, right? The distribution of the trajectory would be with the actual dynamics. So I'm choosing one thing, but then the policy is rolled out with a different distribution, with the policy that I chose, but with a different distribution. So this is a different occupancy measure, right? I choose one thing, but then I run another thing. I can hope that these two would be close enough to each other if I have a good estimate of the transition function, right? If these epsilons are small, then I would expect that these occupancy measures also would be close enough to each other.
It's not clear to me, why do you have to consider include the next state in the occupancy measure?
So this is what helps me to encode also the dynamics here.
But
So
even if you don't include the dynamics, even if you don't include the next state, the dynamics are there, right? Because you have reaching state action.
the dynamics,
SA at
right.
step H.
The dynamics are there. It's not clear if I don't have this. It's not clear how to do the mapping back from occupancy measure back to find the dynamics. And this is crucial for me to define and to show that.
I see.
Yeah, it's not. Yeah,
Because in the previous case, you've essentially marginalized out one of the
exactly.
pairs.
Exactly. The previous case just summing over S
Yeah,
prime. This is
okay.
okay. So this is so the policy is rolled out with this occupancy measure, and the loss we incur, at least on average, is the inner product between the actual occupancy measure and the loss. So this does not fall into the framework of linear bandits, right? Due to this mismatch. I choose one thing, then I run a different thing. So here's what Cohen et al. Did. In the case of unknown dynamics. So they present a variant of linear bandits, which they call distorted linear bandits. So again, we run 40 rounds. In each round, the player chooses an action in RD, but then an adversary chooses a different action for us. Okay, but it's close enough. It's close up to some epsilon to the action that we chose, and the loss we incur and observe is the inner product between this distorted action and the actual loss function. Okay, so in our context, this is going to be the occupancy measure that we choose. The AT is going to be the occupancy measure that we choose, and AT tilde would be the actual occupancy measure. Okay, so they present this variant of linear bandits, and they show an algorithm for it. So it's an algorithm based on the Scribble algorithm. So this is a famous algorithm for linear bandits, which they adapt to distorted linear bandits. And it's not a simple task. Okay, there's all kind of issues that they have there. One of them, so they use a very similar estimator for the loss as in Abernethy et al. But the thing is that whenever you estimate LT using this distorted feedback, it creates bias to your loss estimate. It's hard to control this in the regret analysis. Okay, so this results in a fairly complex algorithm, which at the end gives this regret bound. Okay, and this regret bound is far from optimal, and it's not a very natural algorithm for as an RL algorithm, right? In practice, you're not going to implement this optimization over occupancy measures and stuff like that. In practice, people run other things. Okay, so one thing we want to improve this regret bound, and we want something which is more natural. Okay. So before we'll move on to our algorithm, which is based on the policy optimization framework, let me introduce another definition of the Q function. Again, I guess that many of you are familiar. So first, the value function in some step H and action S is the expected cost from time H to the end of the episode, given that at time H we are in state S. Okay, so this is the value function. The Q function is very similar, but we also condition on the action. Okay, so we are in state S at time H, take action A, and from that point we follow our policy pi. Okay. Okay. And given this definition of the Q function, there's a very useful lemma, which is called the value difference lemma, which breaks the difference between the values of two different policies as follows. So we have here sum over the step. We have expectation over states from the occupancy measure of pi prime. Okay, and then we have the inner product between the difference between pi and pi prime and the Q function of pi. Okay, so it's right. So the occupancy measure here is with respect to pi prime, but the Q function is with respect to pi, and I can replace the two. Okay, so it's not a very intuitive lemma, but it is extremely useful in the context of regret minimization, since if I put here, instead of pi, I'll put here pi t here, and instead of pi prime, I'll put the benchmark policy, the best policy that I'm going to compete with. Then I can break the regret as follows, okay, where this inner sum here for each state and step can be seen essentially as a multi-arm bandit regret with respect to loss vectors, which are the Q functions. Okay, so if I think for some state and step, I'll think of this as a loss vector, right? So the inner product between the policy in that state and this loss vector is the expected cost, like the expected cost of a bandit over A action with respect to this loss vector, and the inner product here is the expected cost of the benchmark policy when I sum it over T steps. this is essentially a multi-arm bandit regret in each state separately. So a natural thing to do would be to run a multi-arm bandit algorithm in each state separately with respect to some estimate of the Q function. Okay, and this is
The previous slide. Is there an expectation of the actions too? So there's a Q function which has an action argument.
here.
Yeah. Is there an expectation over the actions in Q?
This is the actual Q function. I'm going to estimate it
Okay.
somehow. Okay, so at least in the semi-bandit case, this is what was done before. Okay, so you run a multi-arm bandit algorithm in each state separately with respect to some estimate of the Q function. Okay, so one choice of such a multi-arm bandit algorithm would be online mirror descent. Basically, in each state separately, you want to minimize the inner product between the policy in that state and your estimate. I'm not telling you at this point what is this estimate, but the inner product between your estimate and the policy in that state, plus some regularization that keeps consecutive policy close enough to each other. Okay, if I choose this, this BR is the Bregman divergence with respect to some regularization R, and if I choose R to be the negative entropy, then this optimization problem has a closed form multiplicative weight update solution, which basically the new policy would be the previous policy times some weight which decays with the estimate of the Q function. Okay, since we are in losses. Okay, so this is a natural algorithm to run in this case, and the only thing that remained is how to estimate the Q function. So let's see, before we will turn to our case of aggregate bandit feedback, let's see how it was done in the case of semi-bandit feedback. So one thing you can do is to use an importance sampling estimator. Okay, so the estimate of the Q function in S and A would be the indicator that we visit state S in time H in policy T and take action A times the cost to go from time H to the end of the episode, divided by the probability to visit this state in action. Okay, and this is actually an unbiased estimator for the Q function. If you take the expectation of this thing, so the expectation of the indicator is exactly the occupancy measure, and the expectation of the cost to go, given that the indicator is 1, is exactly the Q function. Okay, so this is a good estimate for the Q function, and this is indeed like a similar estimator is used by Lowe et al. In 2021. So they basically run this multiplicative update, a policy update with respect to this estimate of or a similar estimate of the Q functions. And in the unknown dynamics case, this is the result they achieve. Okay, so we now want to modify this idea, and we're actually going to achieve the same regret bound even though we are in a harder setting. So this is the setting of semi-bandit. We're going to achieve exactly the same regret bound even though we have aggregate bandit feedback. Okay. So what have we seen so far? So we introduced the problem of aggregate bandit feedback. We saw the previous approach, which basically uses a reduction to linear bandits or distorted linear bandits. And we reviewed the framework of policy optimization with semi-bandit feedback. Okay, and we want to take this framework and adapt it to the aggregate bandit feedback case. Okay. Now, the hard thing is how to estimate the Q function only with aggregate bandit feedback, right? Because this thing, this cost to go, right? It's the cost from time H to capital H, if I have this for every small h, then I have this for, then I can extract the individual losses, right? The loss in each state. So this is not founded, it's something that I can observe. Okay, so still remains the question, how can I estimate the Q function only with aggregate bandit feedback? And we use a different approach. So instead of estimating the Q function, we are going to estimate different quantities, which we call the U function. And this quantity would be very natural in this context of aggregate bandit feedback. So again, what is the Q function? The Q function is the cost from time lowercase h to capital H, given that we are in S and A, in time h. The U function would be almost the same thing, only that it would quantify the expected cost of the entire trajectory, given that in time h we are in state S and take action A. Okay? So I condition on some intermediate state and action within the trajectory. Okay, so the only difference between these two definitions is whether I sum from time h here or whether I sum from time 1. Okay, and as you might already see, this is much more natural in the context of trajectory losses, right? Because by definition, I have the trajectory loss here. Okay, so what we're going to do now, I'm going to show you two things. So one, I'll show you that the value difference lemma that I showed you before that breaks the regret in terms of the Q function, this can be also done in terms of the U function. Okay, so we'll have a similar regret decomposition only with respect to the U function. The next thing would be how to estimate the U function, only with aggregate bandit. Okay, so let's show the value difference lemma with respect to the U function. So the difference between the U and the Q is basically the cost over the h minus 1 time steps, given that at time h I'm going to visit S and A, right? Because the difference in definition is whether I sum from h to the end or from 1 to the end. The difference would be from 1 to h minus 1, right? So this is the difference between the U and the Q. And note that we are in an MDP, in a Markov decision process, and our policy only depends on the current state, right? So if I already conditioned on the state, the action that I choose is independent of the past, right? If I know in which state I am, the action that I choose, like what happened before time h, does not affect the action that I choose, right? So given S, A, and the trajectory before time h are independent. Therefore, I can eliminate the conditioning on the action. And now this expectation is a function only of the state S. Okay, it does not depend. Here I have the difference between the U and the Q in S and A. And this difference is the same for all actions. Okay, it does not depend on the action. Okay. And now let's look at the value difference lemma from before. This is what I showed you before with the Q function. I want to replace this with the U function. So I'm going to add and subtract the U function. Okay, so I added the U function and then subtract here. There's a minus sign here. Okay. And now this thing again, it doesn't. It's a vector of it's a vector of size A, but has the same value for each action. Right? It depends only on the state. And now here I have an inner product between a probability which sums to 1, and some vector which all of its elements is the same. Okay, so the inner product between pi and this vector is going to be the value in each coordinate, which is the same, the value of WFS, and it doesn't depend on on the policy. It would be the same for pi prime as well. So these two cancel each other. Okay? This term is essentially 0. Okay, makes sense? Okay, and we remain with this thing alone. Okay? And a direct consequence of this new value difference lemma, which now is in terms of the U function, is that we can break the regret of our algorithm as some sum of regrets in each state and action separately with respect to the U function. Okay? So a natural thing to do would be to run a multi-arm bandit algorithm in each state separately, each state and step separately with respect to some estimate of the U function. So this is indeed what we are going to do. So we'll run essentially the same algorithm as before, this multiplicative weight update with respect to some estimate of the U function. I'll talk in a bit how we estimate the U function. So how do we estimate the U function? So again, we're going to use importance sampling. But now we'll plug in here the full aggregate trajectory loss. Okay? Okay, so again we have the indicator that we visit in S, take action A, in time H, times the full aggregate trajectory loss divided by the probability to visit this state and action. Okay, so this is fairly simple estimator, but we needed to discover first the U function for that. Okay, so let's verify that this is indeed an unbiased estimator of the U function. So the expectation of the estimate of the U function, we can apply the law of total probability and write it as the expectation of the U function given S, given that in time H we'll visit S and take action A, times the probability for that, plus the expectation of the estimator given that we are not visiting S or not taking action A, times the probability for that. Okay? And the probability for that is by definition the occupancy measure in S and A. And since I have here the indicator that I visit, the indicator function that I visit S and take action A, whenever I don't visit S or don't take action A, the estimator is 0. Okay, so this term goes away. And now the occupancy measure here from the probability cancels out with the occupancy measure here at the denominator, and we remain only with the full trajectory loss, given that we are in state S and take action A, which is by definition the U function. Okay. Okay. So a few additional details. So first, we don't use this estimator as is exactly. So we need to add some small bias in order to bound the magnitude of this estimator. And another thing is that whenever we have an unknown dynamics, we don't know the occupancy measure. So instead we use some upper confidence bound over this occupancy measure. Okay. And in addition, we also in order to live exploration, we need to reduce some bonus that will essentially would give us an incentive to go to states and action that we haven't visited enough. Okay, so this is also something that we reduce from the U estimate. So at the end, our algorithm would look like that. So in each state and action, I would do this update, which is essentially a multiplicative weight update with respect to these U estimates minus some bonuses. Okay. Okay. So given all that, the way to analyze this becomes relatively clear. So again, the regret, we can decompose the regret as this sum of regrets over the U functions. Since we have a good unbiased estimator for the U function, roughly speaking, and I eliminate a lot of details here. Roughly speaking, we can replace the estimator with the actual Q function with the estimator, the actual U function with respect to the estimator of the U function, and then in each S and H, I'm going to apply some multiplicative weight update guarantee, which are known from the literature. Okay, and there are additional details here. I need to sum in the regret analysis. I need to bound the variance of this estimator, and there are additional details here. But the high-level idea is to apply some multi-arm bandit analysis in each state in the state. Okay, so in the non-dynamics case, this gives this regret bound, a square of square root of SAT, which is optimal in this case, up to logarithmic factors. In the non-dynamics case, we achieve this regret bound, which is it's not okay. We don't know if it's optimal or not. There's a gap between the lower bound and the upper bound, but this still matches the best known regret for policy optimization with semi-bandit feedback. Okay, and also if you consider a broader like all known algorithms, so so again, this is the state of the art for policy optimization with semi-bandit feedback. But this gap, there's a gap of square root of S between the upper bound and the lower bound. This square root of S gap is still an open question even in the semi-bandit case. Not only with policy optimization algorithm, but in general. Okay, so as a summary, we consider the problem of online MDPs with aggregate bandit feedback. The previous work have done this, handled that using a reduction to distorted linear bandits. The regret bound was far from optimal, and the algorithm is not a very natural one as an RL algorithm. We introduced the concept of U function, and this allows us to develop a policy optimization algorithm for this problem. And at least in the non-dynamics case, we achieve the optimal bound. In the non-dynamics case, we get fairly close to what is known to be achievable already in the semi-bandit case. And again, the gaps that remain already appear in the semi-bandit case. Okay, so that's it. This is a link to the paper if you're interested. And thank you.
Questions? I had a question. So you said you match the regret bounds without the aggregate feedback, and you're in the aggregate feedback. So do you have an instance where aggregate feedback is actually harder than the setting when there is no aggregate, when you get immediate feedback?
Yeah. So at least with known dynamics. This is, we know now that this is the optimal bound for aggregate bandit feedback. The upper bound, at least with known dynamics, is h to the power of 3 here. So it's a strictly harder problem statistically. We're not sure yet what happens in the non-dynamics case. It could be.
Are there just missing lower bounds there, or do we have?
So there's a gap. So the best bound using not a policy optimization algorithm, using an occupancy measure based algorithm for the semi-bandit case would be h to the power of 2, like outside the square root, and linear in S, I guess, like in here. This is the best we know, and the best lower bound is with square root of S and h to the 3 over 2. So there's a still gap of square root of hs.
Another question, maybe you already mentioned this, but in your setting, the learner doesn't know what the aggregation length is,
The horizon?
the horizon, yeah.
It does know.
It does
It
know,
knows.
okay.
Yeah, it
Is
knows
it possible to also consider a setting where they don't know?
I mean, if you
Like the feedback appears after some time, but you don't know in advance what that's going to be.
but you know at the end of the episode.
Yeah.
Okay. So I'm not sure. I mean, I don't see an immediate problem, but it might
Maybe
not be
the
a
same
trivial
techniques
thing.
also
Yeah.
gives something. Maybe there's a simple way to connect it.
Yeah, I'm not sure, but yeah.
Any more questions?
There's food downstairs.
Yeah. You can thank the speaker once again.